And it's quite a complicated subject, so I'm just going to kind of keep out all of the details and try to give a overview of the whole subject and the problems we're interested in. Okay, so you may be familiar with quantum groups and the standard quantum groups that became very popular in the late 80s and the 90s. And so today I'm going to talk about a much more general family of quantum groups that are given by quantizing the Poisson groups that are given by certain Lie bialgebra structures on a semi-simple Lie algebra. And these structures were classified by Belavin-Drinfeld back in the 80s. But it's taken us a long time to kind of get the machinery together that we can study them, because as you'll see, it's kind of complicated. Okay, so I'll start with a quick overview, give people an idea before they give up. Then we'll talk about Belavin-Drinfeld bialgebras a bit, because first of all, we need to establish the notation and the ideas. And we also, there's a really crucial result in there about the dual of a Belavin-Drinfeld Lie bialgebra. Then I'll talk about the construction of the quantized function algebra, and similarly the quantized enveloping algebra, though at this point we're getting further and further away from anything that should be called a quantized enveloping algebra, but I'll keep using that terminology because it's very familiar. And then I'll talk about some results and some conjectures. Okay, so throughout the talk, G will be a semi-simple complex algebraic group, and the German G will be its Lie algebra. And we're going to be working algebraically, so we're not going to be talking about formal definitions. We're going to be talking about algebraic deformations. So our parameter is going to be element of C, a non-zero complex number, which generally won't be a root of unity. And as I said, we want to extend our understanding of the standard quantum groups to these more general cases. So the kind of thing that we want to know, or that it's natural to ask, is to classify the primitive ideals of this algebra, because in the standard case, they correspond more or less exactly with the symplectic leaves of the corresponding Poisson structure, Poisson group. So that's a result that we would really expect, that there will be the similar close connection, though there are some issues that we will see come up. Similarly, for the quantized enveloping algebra, there are all the usual questions of whether it has the same kind of finite dimensional representation theory, and whether it has a category O such that the primitive ideals are annihilators of Verma modules, elements of this category, that kind of thing. There's plenty of natural questions to ask, and we expect this this quantized enveloping algebra to have a similar kind of structure to the original one, for reasons that I'll explain. But the structure of the quantized function algebra we expect to be very or significantly different. So here's kind of a brief history, at least of one of these questions, the symplectic leaf question. So in the standard, and this picture also kind of describes the different levels where we want to understand the situation. So we have the leap, well, we start off with the quantum group, which is a deformation of the Poisson group, or the functions on the Poisson group. And the linearization of the Poisson group is this Lie bialgebra. And the level of complication kind of goes in that direction. So the simplest place to look to get a preliminary understanding is at the Lie bialgebra, and then we can push it up to the Poisson group. And generally, the hardest problem is working with the quantum group. So for instance, Thierry Levasseur and I described the symplectic leaves of the standard quantum group, a standard Poisson structure, back back in '93, and we worked on trying to show that the primitive ideals had the same kind of structure, same description, and we fiddled around with some ad hoc methods, but then Tony Joseph came in and kind of came up with some very sophisticated methods that solved the problem completely. And once that was solved, the natural question was to ask, whether the same thing happened in other settings, because there's plenty of other Poisson structures around. So Thierry and I, together with my student Margarita Toro, worked on the multi-parameter case, which was kind of the simplest possible generalization. And that turned out to be fairly straightforward, not of any great significance. But then a long period of quiet happened. So the problem was that we didn't know how to quantize these Poisson groups. It just wasn't as easy as in the classic case. And I'll explain why in a second. So eventually, Ettinghoff, Schedler, and Schiffman in 2000 came up with a really nice way of using the data from the Belavin-Drinfeld Lie bialgebras to twist this standard quantum group and get deformation in the formal setting for these general Poisson groups. And Miller and Yakimov showed that one could extend this and get similar algebraic quantizations. Millen also, around the same time, described completely the symplectic leaves of these things, and it's a complicated description which we don't need to go into now, but which will be the basis for the natural conjectures about the structure of the primitive ideals of this thing. So let me just kind of briefly review what these two, in the standard case, what these two descriptions were. So the symplectic leaves fall into a disjoint union of a finite number of subsets indexed by the double veil group, and each of these sets indexed by W here is a non-empty orbit under the action of the maximal torus. So the elements of the maximal torus are symplectic points, so they naturally act on the symplectic leaves. And almost identical, and we can say a lot about the size of these leaves, etc., but I won't talk about that. So a similar description was given by Tony Joseph for the primitive ideals. Again, they fall into these finite number of H orbits. Beautiful result. Okay, so that's the overview. Now I want to kind of dig a little deeper and how am I getting over time? Good. And we start in this picture over here with the Lie bialgebra structures. Okay, so just in case people are not right up with Lie bialgebra structures and co-boundary Lie bialgebra. So bialgebra, remember, is a Lie algebra such that the dual has a compatible Lie algebra structure. And giving the dual a Lie algebra structure is the same as defining a co-commutator from G to G tensor G. And one way you can do this is as a co-boundary, you fix some element R in G tensor G, and your co-commutator is just the value of the co-commutator at X is just X acting on R using the adjoint action. So a co-commutator like this, I mean, a map like this will actually give you a Lie bialgebra structure if these two conditions hold. The first one is that the symmetrization of R is an invariant element of G tensor G. And the second one is that this classical Yang-Baxter operator is also invariant in G tensor G tensor G. So the easiest way to solve the second condition is to ask that the value of this is 0, which is, of course, invariant. And such situations are called, the Lie bialgebras that we get are called quasi-triangular in that case. And then we have different options given okay, so these elements are called classical R matrices. If we have a classical R matrix, there's various ways that the first condition can be satisfied. One is that this is equal to 0, and that gives us a triangular structure, which actually is not that interesting. The second is that this thing, R plus R21, is non-degenerate and invariant. And this is a very interesting case, which we call factorizable. So we're interested in factorizable quasi-triangular structure, Lie bialgebras. And Belavin-Drinfeld classified these things, and the way they classified it is kind of important. So it depends on two parameters, a continuous parameter S, which we won't talk about, and this discrete parameter, which we call a Belavin-Drinfeld triple. So a Belavin-Drinfeld triple is a subgraph isomorphism of the Dynkin diagram. So we take a map Tor from gamma 1 to gamma 2, where gamma 1 and gamma 2 are both subsets of the set of simple roots gamma, and satisfies these conditions. The first one is the kind of graph isomorphism condition, and the second one is this nilpotency condition, that there's only so many times we can apply Tor to any given element. Eventually, we will fall out of gamma 1. Okay, so let's look at some pictures so that we get a better idea of this. So here's some classic ones here in the AN or A5 case. Gamma is A5. Gamma 1 is the first 4 nodes. And the triple, the map just shifts along by 1 point. And I'll call this the Kremer-Gervais triple because it corresponds to a quantum group that Kremer and Gervais studied many years ago, and turns out to be the quantization of this, the Poisson group given by this Lie bialgebra. Another interesting example is if you have like a G cross G, a product of 2 identical copies of a Lie group. So this is, say, E6 cross E6. So gamma is 2 disjoint copies of this. And so we can send one copy to the other copy. So gamma 1 here is just one of the 2 copies. Gamma 2 is the other copy, and we map one to the other. That's also one that's interesting. I'm not going to talk about these disjoint triples, I don't think, today. Okay, so briefly, some details here that are not particularly important. So the actual R matrix, classical R matrix in the standard case is this object here, the sum of E alpha tensor F alpha over the sum of the positive roots, plus a half omega 0. So when you symmetrize this, you get the classic non-degenerate element of G tensor G, invariant element. And the new R matrices that we get using this data are given by adding a skew symmetric element to the original R. So the symmetrization is the same element still. We've just added some skew symmetric elements. And we do this by, for each power of Tor, we sum up Tor to the K E alpha times wedge F alpha. So not too complicated. This is the condition on this continuous parameter from wedge to H, which I'm not going to talk about because it's not very illuminating. So that's what these classical R matrices are. And so that's kind of finishes the discussion of the original Belavin-Drinfeld theorem from the 1980s. Now I want to talk about an interesting result that says that whenever we have a factorizable Lie bialgebra, well, the dual is almost never factorizable, but there's a canonical homomorphic image of the dual that is factorizable. And on the way to discussing this, we'll see some classic structure that comes out. So given this classical R matrix R, we can define a couple of maps from the dual to G just by evaluating at the first and second elements in this tensor product. So this turns out to actually be both of these maps are Lie bialgebra maps from G star co-opposite, where I'm not going to worry about that either, to G. So we get two canonical images of G star in G, which I'll call P plus or minus, but in the standard case, these are just the Borel subalgebras. So there's nothing hugely complicated going on here. What's interesting is the intersection of these two bialgebras, P plus intersect P minus, which I'll call L. And also, also the push forward of these maps, which is the map from G star onto G star factored out by K. So if we add the kernels of those two maps together, we get a homomorphic image of G star, and this is a factorizable Lie bialgebra. So interestingly, as I said, in the standard case, P plus or minus are just the Borels, L is the Cartan subalgebra, and this is just the dual of the Cartan subalgebra, the trivial structure on it. So it's interesting that actually even a totally trivial Lie bialgebra, abelian, co-abelian Lie bialgebra can have a factorizable structure, but it's kind of trivial. So this is not something that we've really thought about or that was noticed in the standard case, because it only gets interesting when we go into this more non-standard case. So the question is, what is this factorizable Lie bialgebra? And I will now explain how it is naturally inherits a structure from the original triple. So if we have, okay, now let's just work with this picture. If we have this triple, which is the Kremer-Javet triple on A5, and we restrict to gamma 1, obviously the whole of Tor is no longer works because it sends this fourth vertex off to the fifth vertex, which is no longer in gamma 1. So we restrict, instead of taking gamma 1, we take gamma 1 tilde, which is the inverse image of gamma 1 intersect gamma 2, and gamma 2 to be gamma 1 intersect gamma 2. And this gives us a new triple. And in the Kremer-Javet case, for A5, it's the Kremer-Javet triple for A4. And obviously, you can probably guess the generalization of that to AN. And in the double, of course, remember that double one, here gamma 1 intersect gamma 2 is empty. So you'd get back to the trivial triple in that case. Okay, so the big theorem here is that when we have one of these Belavin-Drinfeld Lie bialgebras, its dual has this canonical homomorphic image, which is a reductive Lie algebra, not actually semi-simple. And it's of type gamma 1, and the Lie bialgebra structure is given by this reduced triple. So what I thought was a really nice result I proved many years ago and kind of dropped like a lead balloon, but I'm hoping that it's now going to become more interesting. So for instance, again, in this Kremer-Javet case, if we start off with the simple Lie algebra SLN plus 1, and we take this Kremer-Javet triple, mapping alpha 1 up to alpha n minus 1 up to alpha 2 up to alpha n, then what we actually get is GLN, one size smaller, but the reductive group, and with the kind of associated reduced triple, but also a new continuous variable enters into it. So there's a naturally induced S tilde as well, which I'm not going to talk about. Yeah.
So is L always like the Levy complement of a parabolic or something?
Yes. Something like that.
Okay, or something.
I mean, yeah. Okay, so now we want to take the intuition from that and apply it to the quantum group. Let's see how much time I have. Okay, unfortunately, in the intervening time, we have to discuss a little bit about how we actually do this construction. So it's actually a very simple, familiar process. We twist by a hop-to cocycle. Hop-to cocycle is an invertible pairing, which satisfies this condition in the Sweedler-Hopf algebra notation. If you're not familiar with this, there's probably not much more I can say that helps. So I'm going to describe how we twist with this in a second, but I just want to mention at the same time that it's important to keep track of the co-quasi-triangular structure on this quantized function algebra. So if we were in the enveloping algebra, we're talking about the quasi-triangular structure on this Hopf algebra, but the dual of that, the action of the R matrix on the quantized function algebra is what we call a dual quasi-triangular structure. I'll just call it a braiding for short. And it satisfies these conditions, which are familiar if you know what R matrices are. And if you don't, it's not going to be too helpful. Okay, so the key thing is that given, and this is totally general construction, given a braided Hopf algebra and a 2 cocycle, we can twist the multiplication in this fashion to come up with a new multiplication defined like that. And if we kind of conjugate the original braiding by sigma in this fashion, we get a braiding on this new Hopf algebra. So that's what we're going to do. We kind of come up with a 2 cocycle, and that's going to give us a new braided Hopf algebra, which is exactly what we're looking for. Okay. Okay, so now I'm going to have to describe briefly what this cocycle is. In order to do that, we have to go back and at least think about what the definition of the standard quantized function algebra is. And it's defined as the restricted dual of the enveloping algebra with respect to the category of finite dimensional weight modules. So if we take a finite dimensional module V and pick V and psi from V and V star, then we get a coordinate function C psi V, which is in the dual of U, and the value of that is just C acting on XV. So then for any given V, we have this vector space of coordinate functions, and OQG is defined to be the union of all these coordinate functions, and there's kind of a Peter Weil theorem that says that it's actually the direct sum of the coordinate functions for all the simple modules in that category. So that's how we construct OQG, and that's how we're going to twist it. Okay, now it gets kind of painful. It's that moment when the doctor says this is going to sting a little bit. And you know it's going to hurt like hell. Okay, so okay, we start off with the usual quasi-R matrix or universal R matrix in the standard case. So this is just kind of like tensor of a dual basis where we take appropriate basis out of UQN plus and a suitable dual basis out of UQN minus, and we just add all these things up. So it's an infinite sum. It's in the it's in this closure of the tensor product. But the point is that for any finite dimensional vector space, only finitely many of these terms act in a non-zero fashion. So it makes sense as a coherent operator on all of the tensor products, V1 tensor V2, for these finite dimensional modules. Okay, now we're going to play with this guy by applying Tor to these things here. Well, so I haven't defined exactly how Tor extends to the UQN plus, but it does in a natural way. So we apply consecutively all the powers of Tor to the first variables to get a new object that still is well defined in its action on the tensor product of finite dimensional modules. And in between these things, we have a whole lot of diagonalizable operators, which again, I won't talk about, but they're just kind of, if you have an element on the product of two weight spaces, the action of this thing is diagonalizable with using this bilinear form. Anyway, so it makes sense. It's a little bit complicated. But it also, and so the big achievement of Ettinghoff, Shedler, and Schiffman was to show that this very complicated looking operator actually satisfies this co-cycle condition here. And that tells us that it induces a hop2 co-cycle on the quantized function algebra. So let's get away from that page quickly. So, that theorem of Ettinghoff, Shedler, and Schiffman gives us this theorem that applying this operator J to the V1 tensor V and then applying the Xi1 tensor Xi2, this is a hop2 co-cycle on O of G. Okay, so since this depended on Tor, and actually there was a choice of S here as well. So really, it's not just, well, this should be a pi. And pi is the pair consisting of Tor and this continuous variable S. So that's how we define the new Belavin-Drinfeld quantum group. We just twist by this operator. So this was, so this was constructed by Ettinghoff, Shedler, and Schiffman in the 2000s. And it corresponded with a number of examples of non-standard quantum groups that we already had. So as I said, Kremer and Gervais had defined and analyzed a certain quantum group, and that turns out to be exactly what you get when you quantize using that Kremer-Gervais triple. And similarly, the double quantum groups like the quantum Lorentz group that had been previously studied arose as the Belavin-Drinfeld quantum group for that double, the triple on the double of the graph that I showed in the first earlier. So so everything that we expected to fall under this umbrella fell under this umbrella. Okay, now so then we have to define the corresponding enveloping algebra. But we know how to do this because Fadeev, Reshetkin, and Takhtajan did this in their earlier versions of constructing quantum groups. Whenever we have a braiding on a Hopf algebra, this is a bilinear form, we can fix the entry in the first or second place, and that actually gives us a braided Hopf algebra map from this algebra into its dual. And the image, the subalgebra generated by the image of these two maps is called the FRT dual of a braided Hopf algebra. And that's how we're going to define the general quantized enveloping algebra. So note that this is a very nice construction. In fact, we can naturally join together U plus and U minus using the Drinfeld double, and U of A is actually the image under a surjective Hopf algebra map of these things. So it's a very nicely defined object, and that's how we define the quantized enveloping algebra. Now, if anybody's kind of familiar with finite Hopf algebras, you will immediately think that if we twist the algebra structure on one side, then all we have to do is keep the same algebra and twist its coalgebra structure. Unfortunately, this only works for finite dimensional Hopf algebras. It doesn't work for infinite dimensional algebras. So this thing actually has a very different algebra structure from UQG. And as I think I've said before, we really should heuristically think of this as the quantized algebra functions on the dual Poisson group. But again, I won't get into what that means. So the first result that we certainly would like to know is that this gives us a non-degenerate pairing. In other words, that this thing is a suitably big image, a suitably big sub-Hopf algebra of the dual. And it turns out that it is. And this is an important result because the other thing I forgot to emphasize previously is when we twist using this Hopf-2 cocycle, we don't change the category of finite dimensional comodules. So twisting these algebras is not giving us anything different from the point of view of the braided rigid monoidal category of finite dimensional modules. So from that point of view, we're not getting anything more interesting. And this result tells us that we can pull this all the way back now so that the category of finite dimensional modules over the new enveloping algebra is the same as the one more or less that we started with. So we're not getting anything new. So that tells us as well that we could define O pi QG as the restricted dual of U pi QG with respect to this category. But of course, that's not much help since we don't know anything about the structure of this algebra here. So knowing that it's the restricted dual of an algebra that you don't know anything about is not that helpful. So now I want to talk about how U pi QG compares with the usual UQG. And in particular, the triangular structure of UQG. You know, the UQG is kind of has a U0, a Cartan component in the middle, and then it has two Borel components, and it's generated by those two Borels. So that's U plus and U minus are the two Borels in that situation. U0 is the Cartan part. So we have, in general, exactly the same kind of thing. And there's a trivial way in which there's a braiding on U0. So whenever we have one of these FRT duals, this center U0 is a braided Hopf algebra, which in the standard case is just this kind of Laurent polynomial ring, so it's not anything particularly stunning or interesting. But it turns out that it is much more interesting in the case of these Belavin-Drinfeld quantum groups. So yeah, in this last example, I just said what I... Okay. So now I'm going to lift some intuition up from this picture that I was just describing. So if you remember, when we had this Lie bialgebra, we had these two maps, phi plus or minus, which map to these p plus and p minus. And then they kind of push forward to G tilde, which was factorizable. And it was this, you know, Belavin-Drinfeld object associated to the reduced triple. Similarly, on the other side, inside G, we still have these two sub-Hopf algebras, and we have their intersection. And their intersection turns out to be is the dual. So this kind of pull back is the dual of the push forward here. then we can lift this up to maps on the corresponding Poisson groups. And so then heuristically, we just take, we just kind of assume that this is functorial in some way. So we take the deformation, the algebraic deformation, and we hope that something like this happens. So what is going on here? So now we're having this triangular decomposition of u pi qg, but u0 is a quantized algebra of functions on this smaller reductive group associated to the reduced triple. So the u0, instead of being this very simple Cartan piece, is a very complicated object. And these objects are, yeah, well, what's anything about that? And similarly, on the other side, we have O pi qg mapping onto the functions on its two parabolic subgroups, and then that pushing forward to this object, which is now the algebra of functions on the group dual to the reduced G tilde. So according to our intuition, again, this should be the quantized enveloping algebra with respect to G tilde. So again, this is just to kind of ground you again. This is what would happen in the standard case. We're just talking about embedding U0 in the two Borel parts. And over here, we're just projecting onto the Borel subgroups and then onto the torus. I think my notation for the torus changes from H to T to K. Sorry about that. I keep pulling stuff up for different talks, and obviously I changed my notation. So what do we know? We still don't have the answer about the U0, these two pieces, though it seems very likely that it holds. We do have a definition, a very natural definition of O pi q p plus or minus. We define it like this. In order to define O pi q p plus or minus, we actually use the old UQ p plus or minus and take the things that vanish on that. Turns out that that's exactly the kernel of these maps. And so this identifies U plus or minus with quantized functions on these parabolic subgroups. And it also, interestingly, if we combine this with delta, we do the map L plus tensor L minus from O. No, that should be pi. It should all be pi, sorry. This gives it, this is an embedding from O pi qg into the tensor product of these two things. So that's kind of analogous to saying that P plus times P minus is a dense subgroup of G. But the really interesting result, let me go ahead to this one. Well, the really interesting result is that this U0 should be kind of an opposite type of object. And we certainly have evidence for that. In the Cramer-Gervais case, we know it happens. For the double quantum groups, we know it happens. So in all the examples we've observed, it works. So we expect it to work in general. But even more interesting is that dual to this is this homomorphic image, this surjective map from O pi qg onto this enveloping algebra. And this, when it sinks in, is a very interesting statement, because now if we try to describe the primitive spectrum of one of these objects, we're going to also have to describe the primitive spectrum of any homomorphic image. In other words, describing the primitive spectrum of O pi qg will include describing the primitive spectrums of UQG, which was a similar problem to describing the primitive spectrum of U of G. and is itself a real challenge. So somehow this is like an all-encompassing challenge, because the two, what used to be different worlds, the enveloping algebra and the quantized function algebra, are now kind of joining together and melding together so that one occurs inside the other one and the other one occurs as a homomorphic image of the quantized function algebra, etc. So that's the challenge for the next couple of years, to solve these problems. Thank you very much for listening. I appreciate your patience. Yeah.
Yeah, so you mentioned that these conjectures sort of come from just like blindly hoping that some factoriality holds, and then applying that to the thing that we know holds pre sort of quantization.
Yes.
Do you know if there is some even very weak factoriality that does hold? I mean, the procedure was very complicated on that slide. That was like the doctor's office visit.
Yeah, but we don't really have any functorial approach to it. Like in the standard classical case, we just use it as a guide, and then we apply Hopf algebraic techniques to prove our result. And yeah, this is one of the really interesting questions, is whether we can have a more functorial approach to things and just quantize these symplectic leaves into like localizations of factors of the yeah.
And do you think that that's too naive or optimistic, or do you think there's a chance that something like that works?
Well, it certainly hasn't worked for the last 20 years. So it needs a genius to come up with something. I mean, there are functorial constructions, like the Etinghoff-Kazhdan deformations are functorial, but you can't really get your hands on them in any way. And I don't know, maybe they're like the problems that Alex was talking about occur. Yep.
So you mentioned, or like the slide mentioned that we do this quick thing, like quasi triangular algebra, you get like the same, the category of comodules doesn't change.
Right.
But like under the FRT duality, it does. I'm guessing the category of modules does change. Is that right?
Well, not finite dimensional. No, because once we have this condition, the category of comodules transfers over to a category of modules over U pi QG. So the category, instead of kind of going directly from one enveloping algebra to the other one, it goes from modules to comodules, takes the twist, and then goes back. But it's still preserved in all these steps. So yeah, nothing is changing there. It's the infinite dimensional representation theory that's going to be interesting.
What about tensor product of modules?
No, it's equivalent. Yeah, so the braiding, it's naturally equivalent as a braided category.
So instead of using the FRT construction to get this U pi from the twisted O, would you construct a twisting in the form of the Etinghoff-Shedler-Shipman on UQ?
No, you definitely can't do that. You can do it in the formal sense, but not in this algebraic sense, because the co-algebra structure goes off. It doesn't land inside U tensor U, it goes off somewhere else. So it doesn't induce
The conceptual explanation.
yeah, I mean, basically it never works in infinite dimensional Hopf algebras. This is definitely a feature only of finite dimensional Hopf algebras, that the co-cycle twist works on the co-algebra structure. I mean, if I could say one more thing, I mean, when we think about the construction of UQG, we kind of basically start off with U0, and then we throw in the E's and the F's and put in relations. And so you might ask, can we do that for the U pi QG? Can we start off with this U0? can we start off with this thing and then construct kind of in a Lustig fashion the enveloping algebra from it? And probably you can do that, but unfortunately it's kind of an inductive process because you need a definition of this thing before you start. And if you want to define that as a restricted dual, you first have to define the U. So it becomes this kind of ladder of definitions. Sorry, that was more than you asked.
There are more questions. Doesn't seem to be the case.
Okay, thank you.